Now let me just use contact tool. So now what is this contact tool? Is this contact tool? This is a uh, this contact tool will give us initial information about the contact. So instead of giving contacts and solving the problem and coming to know that there is a some bit of error or problem with our contact that we have missed during the uh, selection of contacts. So this is a tool which will ensure that everything is correct with the contacts. So it will save our computational resources and the time. Uh, so we can check the contacts if it is everything is correct or not before solving the problem. So if you see here initial information. So now if you see initial information, so one thing is there is a we have three contacts and three target, totally six thing. So now any other than white or gray, any color appears, there is some error in the contact and we need to rectify those error. So red has here you can see red indicates this, yellow says the contact is open, orange is contact is closed but has a large amount of gap or penetration. So now if you see here in the contact region, here you see geometrical gap is 0.2 mm and the gap is 0. So this is the geometrical gap which is there, which is the which is comes with the geometry. So this is the geometry gap. That's the clearance we have in that from blank to die. That is a zero point 0.2 of clearance. That is geometrical gap. But since we used interference treatment, that is adjust to touch, that gap is filled up by the solver so that it is 0 and it is zero point 0.2 and it is 0 and it is 0.91, almost close to zero point 0.2, and it is some 10 to the power of minus 30. So consider it is a 0 and there is somewhat penetration between this component and those penetration is in the order of 10 to the power of minus 2, so we can neglect those. So everything is correct. So this is a resulting symbol. So now let's get back to mesh. Here you can see the mesh is automatically generated because we have used this contact tool. So this contact tool works using the mesh. So whenever you don't give any mesh, it will take default mesh and generate a mesh, and with that mesh, it will gives us initial information about the contact. So we'll change this mesh sizing, select body, and say element size as 3. You can also use smaller element size, but due to the solving time and the computational resources, I am using 3 mm. So you can use whatever element you like. You can also further reduce this 3 mm. So now fresh meshing. So now apply. So now we'll use another fresh meshing. So this fresh mesh is used when you need a uniform or regular mesh. So this time I'll be using this. And as you also see the previous generated mesh, for the blank, it is throughout the body. But for those components which are rigid bodies, the mesh is generated at the surface level, that too at those surfaces which are involved in the contact regions. So that's the reason we are using rigid bodies. So we'll get pure mesh. Pure mesh means less computational resources and solving time. So we'll just say update. Now it is completed. You can see the regular mesh or the mesh is generated, and this is a blank. So, okay, now just okay, mesh is completed. Now we'll give boundary conditions. So the first rigid and sorry, this die and the blank holder supposed to be a fixed in their place. So now we'll be using remote displacement because fixed support will not work for rigid bodies. So now let me just duplicate it and one more time. So apply, say enter 0, enter 0, enter 0, enter 0, enter 0, and enter 0. So now all the degree of freedoms is set to be 0, which will gives us fixed support. Now same thing will be done for blank folder. 0, 0, so all the 0 you can also see here from graphics window. 0, 0, 0, rotational zeros, 3 zeros. Now for the punch we'll use 0, 0, 0. It will be free 0. The y component is free because our punch has to travel downward direction. So now let's come back to analysis setting. Here we have here by default the number of steps is 1. We'll be using 10 number of steps. Select all the steps. Auto time stepping on sub steps. So now here 60, 40, 100. Now from 7, 8, 9, 10, the steps will be 80, 52, 150. Now one more time select all the step. Select large deflection. This large deflection kept enabled the large deflection. This is because our blank geometry is significantly changing. So that's the reason the stiffness value changes. So to account those all those things, large deflection should be enabled. Control, restart control, go to manual, load step all, and that's it. Okay. Now, so number of steps. What is number of steps? I'll tell you in terms of punch displacement. So if you see here, we have 10 steps. Step number 1 is 2 times repeated, but this is step 1 at the beginning, and this is a step 1 at the end of the step 1. That is at the end of the particular step. So here you see, right, change from free to tabular. Now you see y component, all zeros, change it to minus 50, minus 5. So now you see the y displacement starts from 0 to minus 5 to minus 10 and so on up to minus 50. Although our displacement is minus 50, but what we are doing is we are applying the punch displacement in a gradually applied manner. So instead of applying 50 mm of displacement in one step, we are applying in 10 number of steps, which will acts like a gradually applying load, just like that. And we have also used this substep. What is this substep is, at this step 1, we are supposed to we are supposed to complete 5 mm of displacement of that punch. So this again, this 5 mm of displacement is again gradually increases in at a 60 interval because we have gained 60. So minus 5 divided by 60. So whatever the value comes, that little mm of displacement is keep on adding, gradually adds up. That is substep. So we have I have also used what is a number of steps, what is multi steps, and what is sub steps in a video. The link of that particular video, you can check it out in the description as well as in comment section. I have explained it briefly. So now coming to solution. Now we'll add strain, stress, equivalent plastic strain, and deformation, that to directional. So for directional deformations, as we are only interested in the blank blank, what is happening to the blank, so we'll just change geometry to blank, and here orientation is y-axis because the blank will be mm, moving towards the y, so deformations will be in the y direction. So now plastic strain, change it to blank body, same, similar to do this strain. So now almost everything is completed. All the loads and set of values is completed. Now we just have to solve. Before solving, we'll just update this mesh one more time. So nothing is changed in the mesh. It just, as you changes the analysis setting, it will ask you to update one more time the mesh. That's the reason. So now we'll just solve. So now go to solution information and change solution output from solver output to force convergence. Now here you will see two lines or two graphs. One is force convergence, the other one is force criterion. So this part, this for the convergence will happen whenever this force convergence drops below this force criterion line. So as you can see, at 10th value, from 9 to 10, it started to drop below force criterion. So at that level, the convergence started to happen. But uh, this is the convergence right now is happening at the substep level. So now if you come to analysis setting, and if you see for step 1, end time is 1 second, and step 2, end time is 2 seconds, and so on like that. Step 10 step and end second is 10 seconds. So but this has nothing to do with our solving time. This is pseudo time. So now to complete first step, our time has to hit 1 second. So until that, all the convergence is happening at the substep level because uh, step 1 is not completed, is about to get complete. It's 0.8. So when the 1 second happens, the convergence happens, but not at the substep level. Right now, all the convergence is happening at the substep level of step 1. Now, step 1 is about to complete. At that step 1, again the convergence happens, but it will be at the step level, that is load step converged, because at that step we have given some load, that is, in our case, that is 5 mm of displacement minus 5 mm of displacement. Now, here you see 1 second, we have uh, dark blue line says load step converged. That is at 1 second, we have step 1. That step 1, at that step 1, whatever the load we have given, that with that load, convergence happened. So that is what this graph is trying to tell us. So now it will just keep on calculating until step 2, step 3, up to so on, and step 10, until the step 10 gets completed. Then our solution will get completed. And another reason to use this substep and number of steps is for easier convergence. So to avoid any convergence issue, we'll increase the number of steps and number of substeps. By doing so, we'll avoid any convergence issue that will happen during the simulation. So one advantage of this using number of steps and the substeps is the convergence will happen very easily, and there will not be any convergence issue. If there is any convergence issue, we need to again change the number of steps and number of substeps, and then once more again we need to solve the problem. So now our solution is completed. Now just look at some results. So when you say scoped body, you'll get the only blank results. See, that's the elastic strain. This is stress, this is plastic strain, and this is deformation. And this is animation of what is happening. And you can say no wireframe. You'll get the results without those elements. And you say all bodies, and you'll see how this thing. So now here under you see there is a tabular data. Uh, those are at what instant of time. What was the minimum strain, maximum strain, and the average strain? Same for the stresses and plastic strains and deformation. So now you have something called report view. So what this will does is it will generate the report from top to bottom, from geometry to the directional deformation, and everything will be in this report. So from unit system, what kind of unit system you have used for what was the geometry, what was the parts, what was the material, um, what type of properties the material had, and the unit system and the symmetry conditions. So what kind of symmetry you have given to which uh, component you have given symmetric, and the contacts, contact regions, and the contact tools, everything, whatever till now you have just given everything. Mesh, what was the mesh size, how many nodes were generated, how many elements were generated using the mesh uh, size, and what was the loads and boundary conditions, what type of analysis setting has been given, everything, every data which we have just given will be in this report. So now this is results. So now if we'll just jump back to results. So this is the results. These are those tabular data of elastic strain. Like that, you'll have every data. And if you want the image of this particular, so I mean the result file, you can just go and say image, and you'll have the image, and just say image to image for stress. Now just generate the report file. Then you'll have the image as well in your report file. So coming to stress. So this is elastic strain. At the end of the tabular data, we have results. So this is a result file or image. So like that, we'll have everything, and you can just create a PDF through it. You can create a PDF and you can use it for future references.